Stanford University.
So I'm happy to see a fair number of people came back for more, so thank you. So this is the second of 2 lectures. The first was last week, and the title is, of both of them, was From Black Holes to Superconductors. Okay, and so let's remember what we did last week. So last week we said 2 things. Well, we said many things, but they fall in 2 categories. So the first thing we said was that there's certain, let's call them unconventional materials or difficult materials, or many body systems, let's just call them materials. And these included high temperature superconductors. High TC superconductors. TC is the critical temperature where they become superconducting. And what was difficult about these materials, we said, is that they were caught between order and disorder. So they're neither ordered. And so remember, when we talked about order, the thing we sort of had in mind was a solid, okay, of well-arranged particles that are fixed in a certain place by their interaction with the other particles. So they're neither ordered nor disordered. Where by disordered, we had in mind something like a gas, where what was dominating was the kinetic energy of all the particles. And so they were all moving around all over the place, but relatively independent of one another. And these things that were in between, that were neither ordered nor disordered, we called them liquids, or more particularly quantum liquids. Okay, and so that's the set of many body systems that we're trying to get a handle on, okay, because we're not sure how to think about them. Yeah? All right. And then part 2 that we talked about last week. So we said a few things. We observed the black holes. Classical black holes we said that they have thermodynamic properties such as entropy. And they obey things like the first and second law of thermodynamics, so thermodynamic properties. Get your entropy. Right, the entropy was the size of the black hole. And right, okay, very good. And so the second law of thermodynamics was the fact that the entropy would always get bigger. And also we discussed that if we probe them, so if we throw a pebble into a black hole, we said that it would behave, that certain ripples would form on the surface of the black hole, and it would behave just like a quantum liquid. So when probed, we saw that they behave like a medium, where the characteristic time scale, okay, at which things happened, was h bar over t. And the point about that time scale is that it's neither long nor short in a way we defined last time. Okay. And so this fact of not having a long time scale was this idea of it being in between order and disorder. So the particles, when they're disordered, because they basically don't see each other, so they travel a long, long time before they occasionally bump into one another, right? That was this disordered case. Okay, so this is what we said last time. Were there any burning questions from last time that I should address? Yeah.
Yes. I operate. What do you mean? I mean, it's still very low, right? But it's still very cool.
Sorry.
I operate superconductors.
Yes.
It's still very low, right?
That's right. So high.
I mean, I'm trying to figure out what's high.
Oh, I'm sorry. Good. So these high TC superconductors become superconducting at let's say about 100 Kelvin, which is about minus 200 degrees centigrade. So it's cold, yes. But, okay. Firstly, this is much bigger than, let's say, 10 Kelvin, which was the highest that existed before the 1980s. Okay, so superconductivity was discovered, almost 100 years ago. Well, in fact, about 100 years ago. So for 80 years, the critical temperature went from, let's say, 4 to 10 Kelvin. And then suddenly in the 80s, there was a revolution of new materials discovered, and the temperature suddenly jumped up. The maximal temperature suddenly jumped to 100 Kelvin. So even though they're low by sort of our everyday standards, it's high compared to all other materials. Okay? Yes?
Yes. In regard to this last thing of throwing a mass into the black hole, and you described ripples on the surface. Okay? And I'm confused about this because the event horizon is imaginary. It's a if you threw me into the black hole and I cross the event horizon, am I going to observe ripples as I pass this imaginary bound?
Excellent. So that's a very good question. And so when I'm talking about black holes, it's going to be from the perspective of somebody that's standing outside the black hole and is boosting with all their rockets to stop falling in. So the picture is here's our black hole, and we have somebody sitting outside, and this person is not falling in. Okay? And then this person throws the pebble into the black hole, and if they had a precise enough apparatus, would see space-time sort of would see space ripple. Okay? So for example, I don't know how, with being theoretical here, so let's say you somehow had a whole bunch of little spaceships that were boosting just outside the black hole and not falling in. Okay? When you throw the pebble in, you'd see those little spaceships bounce up and down a little bit. So that there really is a sense in which there's a ripple of gravity going around the space just at the surface of the black hole. So that's the sense in which it's a ripple. But it's true, to actually see that ripple might not be the simplest thing in the world. And right. But this is all from the point of view of somebody standing outside the black hole. Okay? And where it's definitely, yeah.
Yeah, you're talking about ripples in space, not ripples of material.
Well, that's right. And so that's right. So the interesting thing, and this is sort of what we're going to talk a little bit about today, is that these ripples of space, if you make certain identifications, like the total area of the black hole is the entropy, and the mass of the black hole is the energy, and so on, then these ripples behave as though they were a medium. But at the moment, they're not a medium. It's just space with a empty space. In fact, if you fell through the horizon, you wouldn't even notice it's there. So at the moment, it's sort of a mathematical analogy. Okay. Yeah.
So last week, those ripples were described in terms of charge diffusion, but if we eliminate the charge for a second, just because space-time...
It could just be energy itself that would also diffuse, of course.
Is it by that same model that you gave, the diffusion equation? Or
Yes.
is there something else?
Any other questions? Okay, so this week, indeed, the objective is to make this connection a little bit more precise. So the objective for today is to describe the connection between these two things. So at the moment, I would say where we left it off is that there's sort of an analogy. Okay, so today we'd like to describe a precise connection, although our description will not be totally precise, but it does exist. Describe a precise connection between these two things. And do some things with it. And so to do that, I need to start with a new concept. So step one is I want to talk about the concept of duality. Okay, so this idea of duality is going to be the way these two, it's a certain relationship between things that I'm about to describe. Okay? Right, so first up is duality. All right? So the word duality is used for lots of different things, so I want to describe a particular one. So conventionally, for most of its history, although not always, science has been reductionist, right? So the objective of science is that there's this very complicated world all around us, and we'd like to identify some simple building blocks and understand the complexity that we see in terms of simple building blocks behaving in simple ways. And then you can imagine that when you put them all together, they do something complicated, right? So let's say traditionally, or maybe that's a loaded word, but much of what science does is reductionist. And as I said, what that means is you try to understand something complicated in terms of something simpler building blocks. And this idea might go back, I don't know, maybe to Democritus, who introduced the idea of atoms. Purely theoretically, of course, right? He said, you know, if you have a tree, the tree burns and it becomes smoke. It can't be that the tree just disappears and the smoke appears from nowhere. There has to be some continuity, so maybe there's some basic building blocks that are much simpler than either the tree or the smoke, and that they just rearrange themselves when you burn the two things, okay? And so that's the essence of the reductionist idea. And I'm afraid I can't resist to go on a slight tangent here. And it was just a theoretical concept, right? He had no evidence, no experiments. It's just that something had to be continuous. It didn't have to be this way, actually. There's another Greek guy, it's a bit of a tangent, but it's fun, called Anaxagoras. Who, faced with the same problem, came up with another solution, which is that clearly the tree must somehow have smoke in it, and smoke must somehow have the tree in it. And so everything must be in everything in some way. And that what would dominate is that sometimes a certain aspect of a thing would be expressed and other things would be repressed. And we might think now, well, he was just an idiot, but he got it wrong. But that's not the right way to think about it. The right way to think about it is those are two perfectly good logical solutions to a problem that existed at the time. And in fact, I don't know how often this point is made, but Anaxagoras wasn't wrong. So we think about genetics. Our genes have all the different, a single gene can become your brain, it can become a muscle, it can become a bone. And everything's in a single gene, but it's expressed in different ways, right? So there are maybe circumstances where Anaxagoras got it right and everything's contained. If you take a cell from your skin, you can make a bone out of it, right? But in physical sciences, this has been the paradigm of how things work. So another way of thinking about these liquids or quantum liquids are situations where this becomes complicated. So in liquids, which I'll always include this sort of quantum. Remember, quantum liquid was one where this transition between order and disorder wasn't due to temperature making things vibrate, but due to the quantum tendency for things not to be at a clear place was responsible for disordering things. So these liquids are precisely cases where it's not clear what the useful building blocks are. So you might say, well, certainly we know that the charge in a metal is being carried by electrons. Okay, there's no doubting that. However, a single electron in this quantum liquid regime, you might try following a single electron. It's going to move a tiny distance, and suddenly it will collide with another electron. And then all these electrons are going to go off in all kinds of funny directions. And if you try to describe the transport of charge in terms of these supposed building blocks, you're going to find that it's very difficult because they're all interacting with themselves in a very complicated way. It's completely analogous, in fact, to say water in a turbulent river. Okay, so you've got river, and you could say, well, sure, the water's made out of molecules of H2O, but if you try to keep track of what a single molecule is doing, it's going to be doing something very complicated. And so, whilst sort of at a material level, the molecules of water might seem like they are the building blocks of the water. At a sort of explanatory or understanding level, they're clearly not, because every molecule of water is doing something very confusing. Yeah, so this is, for example, the molecules of H2O in a turbulent river. So again, here it's not that reductionism is wrong so much that it doesn't seem to be useful. It's not, we think we know what the building blocks are, but the building blocks themselves are behaving in a very complicated way, okay? And the idea of reductionism is that when you look closer, things are meant to get simpler, right? The building blocks are meant to behave simply. So duality is try to be a way around this, and duality is going to be which we'll be precise about in a second, is the idea that given the system, there's not a unique choice of what you could think of the building blocks and what you think of as derived from the building blocks, okay? So we'll make this precise. So duality is going to be the idea or the notion that there's not a unique choice of what you think of as the building blocks. So the notion that a physical system admits many different descriptions. So I'll give you an example right now. Okay, but the idea is that, well, okay, so the picture, the sort of artistic view of this, and now we're going to see why I didn't study drawing. But so here's some picture. What am I trying to draw? A face? Okay, with apologies. Okay. So I'm sure you've all seen this picture that looks something like this. And, you know, is it two faces or is it a vase, right? So, or neither. So you want to, so and the flip between, so this is the idea, it's called a Gestalt switch, which is that this is given. It is what it is. It's a picture with black and white dots on it, okay? There's no ambiguity, but there are two ways of thinking about it. You either see the white as the background and the black as the foreground, in which case it's two faces, or you see the black as the background and the white as the foreground, in which case it's a vase, okay? So this analogy is pretty good, as we'll see in a minute, okay? So it's going to be a flip. What's made out of what? Okay, what's the background and what's the foreground? So that's really the essence of duality. So I'm going to give sort of two examples. So the idea, of course, is going to be that these materials and these black holes are going to be dual to each other, right? That's where we're heading. But we need to warm up first. So let's do an example. That was not good. Is that okay? Yeah. So, example. So we're going to contrast the behavior of two theories, physical theories, that look somewhat similar and yet different. So we're going to contrast, in fact, let's see if we can fit this on one board. So we're going to have quantum electrodynamics, okay? So that's the theory that describes electrons and light, okay? So for example, this theory will tell you why metals look shiny, okay? That's the electrons in the metals interacting with the light, all right? And the other, we're going to contrast this with what's called quantum chromodynamics. That's the theory of quarks and gluons. So quarks and gluons are not quite as everyday as electrons and light, but quarks are what protons are made out of, and gluons are the things that bind the quarks together, okay? But let's start over here, where we're a bit more familiar. So light, you might know, is made out of photons. And so photons are the quanta of light. Okay, light isn't continuous; it comes in packages of energy, and those packages are called photons. And so, right, and so now, you're also probably familiar with this picture. Suppose I have a positive charge and a negative charge. So, for example, this might be an electron. In some convention, let's say electron. This could be a positron or a proton or something with a positive charge. And then what you get between these are field lines, right, which look something a bit like this. Right? These are the force lines of the electric field that go from one to the other. Okay, and as you might know, if you have two charges, there's a force between them. So the force between these two charges that goes like 1 over r squared, where r is the distance. Okay, so if you have two forces, a positive charge and a negative charge, a certain distance apart, if they're attracted to each other, if they're opposite charges, and the attraction is stronger the closer they are together, and weaker the further they are apart. Right? That's what it's one of. So if they're very far away, this is small. If they're very close, it gets bigger. All right. So these things here are called, these are the electromagnetic field lines. So I'm doing here the case of charges. You could also have a magnet, okay, and then these would be your iron, the iron filings that form this kind of pattern. Those would be the magnetic field lines. Okay, these are electric field lines. Now, in quantum electrodynamics, what's responsible for this force between the two charges is actually light itself, or photons. So one can actually think of these field lines, in fact, one does think of these field lines as being made up of lots of photons that are sort of flowing back and forth between the two charges. So the field lines, these electromagnetic field lines, are in fact made up of photons. Okay, that's just the facts. Okay, that's what photons do. They're not anything different from these field lines. Now, quantum electrodynamics, was actually discovered in the 40s, way back, and it works extremely well. And the reason it works well is that it turns out that these photons, they don't interact very strongly. Okay, so if I've got a charge here, it'll start sending some photons off to talk to the opposite charge, okay, along these field lines. But it does that at a relatively weak rate. Okay, so these photons don't interact too strongly. That's just a fact. So if you like, the photons are sort of on the gas side of things. They just move between the positive and a negative charge, and they don't really interfere with, in fact, they don't interfere with each other at all. Okay. Now, quantum chromodynamics, on the face of it, is a similar story. You'd have a quark, so that's a certain subatomic particle, and you could have what's called an antiquark. Doesn't matter, it's the same thing. It's just a quark. Antiparticles are nothing mysterious. They're just the same as particles with a bunch of properties reversed, like the charge, like the sign of the charge. The only mysterious thing about antiparticles is that for some reason we're surrounded by particles and not antiparticles. Okay, that's not totally understood thing, but in principle there's nothing mysterious about antiparticles. They're just particles like any other particles. Okay. So now if you take a quark and an antiquark, then they interact by exchanging gluons in the same way that these guys, the two charges interact by exchanging photons. And so we start drawing gluons from one to the other. However, there's a big difference that these gluons do interact very, very strongly with themselves and with the quarks. And what happens is that the field lines don't look like this. These are sort of floppy, okay? They're going out all over the place. The field lines here directly connect. They're sort of all concentrated like that, okay? And what that turns out to mean is that the force as a function of distance between a quark and an antiquark, it doesn't get smaller as they grow apart, but it stays the same. So the force is constant. Okay, so I have an electron and a positron. I might have to work a little bit to start pulling them apart, but once they're quite far apart, I can just move them and nothing happens. With this quark and antiquark, I just have to keep pulling, and it never gets easier. Okay? And this turns out that if you go through the equations, that it's manifested itself in that these field lines are very concentrated between these two. So this thing is called a flux tube. Okay. Good. And in fact, this is a famous name. This is related to what's called confinement. And this explains why you and I have never seen a quark. Okay? The quarks don't float around. Well, not that we've ever seen an electron either, but we could in principle if we looked in the right place. But we'll never see a quark because the quarks and antiquarks are so tightly bound together that they never appear separately. They only appear as protons and neutrons inside the nucleus. And that's because of this very, very strong force that binds them together. Okay. So, this was from the 40s. But in the 70s, people wanted to try to understand this theory. Can we understand the behavior of gluons and quarks? And they were running up against this problem that everything's interacting very strongly. The forces never you can imagine, if the force is constant, however far apart they are, if you have a whole gas of quarks, they're all talking equally to themselves. Okay, so that's clearly a much more complicated problem than many electrons, which when they're far apart, they don't interact so strongly with themselves. Okay, so clearly, we have a whole gas of quarks and antiquarks and gluons is going to be very complicated, right? Because the interaction doesn't get weaker when they get further apart. And so one idea that arose in the 1970s, actually Lenny was one of the people thinking about this, was that what if we don't try to describe this system in terms of the quarks and the gluons, but we try to take the string itself as the fundamental object, okay, this flux tube. So there's a very rigid, because the force is so strong, this sort of string is a very rigid object. It has a big tension. So the idea was, what if the string itself, the flux tube, is more, let's put in quotes, fundamental than the quarks or gluons. Okay? And then how do we do that? So we started off, somebody wrote down, inspired by this case. This case is weakly interacting. So you write down some theory that describes how all these things interact. Now someone sort of basically copying that model wrote down a theory for how quarks and gluons interacted. But it turned out it was very complicated. No one could solve the equations. Now what if actually the fundamental object is the string, and that maybe the string can wiggle a little bit, the same way that we can send a wave down the string by shaking it, and these wiggles would actually be the gluons, for example. And so, right. And so this was actually the origin of string theory. Although string theory then went off in very different directions. The idea was that we shouldn't try to understand QCD in terms of quarks and gluons, but maybe in terms of these strings. And so then you could ask, well, look, I'm confused. What's fundamental here? Is it the quarks and gluons, or is it the strings? And the answer is either. Okay? So either. So actually, both of these systems, in fact, you can either say the flux tubes are fundamental and the particles are derived, or it's the other way around, right? The particles are fundamental and the flux tubes are derived. So the point of duality is that it's possible to, and I'm going to be even more precise in a minute, it's possible to think about it either way, and it's your choice. So if you want to study quantum chromodynamics, it turns out that it might be better to think of the flux tubes as fundamental. Now, if you try to describe quantum electrodynamics using the flux tubes, that's very hard because, as I mentioned, these flux tubes are very floppy. They're not rigid objects, and it turns out the equations for the flux tubes here are very difficult. So depending on your problem, you get to choose what you think the building blocks are. That's the idea of duality. There's not a unique fundamental thing out of which everything else is built, but it's your choice. Okay? And this is very anti-reductionist. Okay? This is like saying, actually, I think I heard Lenny say this once. This is like saying, normally we think of a house being made out of bricks. Okay? This is like saying you sort of think of the bricks as being made out of the house. Okay? That's except it makes sense in this context. Okay. So let me, just in case this sounds a bit mystical, let me give you a very down-to-earth analogy.
What I said was that anybody who thought that was
Okay. Great. Good. All right. So I'm going to make this a little bit more precise, and to do that I'm going to use a tiny bit of calculus. So this is going to be just a 5-minute interlude. It's going to have some calculus. I understand a lot of people here took a math class at some point in their life, maybe recently. So if this doesn't make any sense to you, just tune out for 5 minutes, only 5 minutes. But it's going to make this very clear, I think. So what a duality really is, it's a change of variables. It's completely equivalent to a change of variables of the sort that you might do when you're doing an integral. So let me explain this, what I mean. So let's say you've got a hill that happens to be Gaussian shaped. Okay, it's a two-dimensional hill. So it looks something like that. All right, this is the x direction. That's the y direction, and there's just a bump there. Okay, and it has this shape. And I want to know the area underneath the bump. Okay, so everything's flat. Got a little bump here, how much sand is making up that bump. Okay, that's my question. All right. So in calculus, that's an integral. That's what an integral is. So the area under this bump is, we'd say, we integrate over x and y, means we sum over this direction and that direction, the heights at each point, right? And let's pick it to be Gaussian, which is this particular formula. Okay, this is a formula that expresses this bump, okay? Again, this makes no sense to you, just leave it for 5 minutes. So you have to do this integral. So this is a technical problem that we learn in high school or in undergrad or somewhere to do this integral. Now, if you see this integral, you might not know how to do it the first time you see it. Okay, in fact, maybe it is difficult. And so what is this integral really doing? What we've done is we've taken the plane, the x and the y directions, and we've split it up into little square bits, right? And then we're calculating the height of each little bit, and then we're adding them up, right? That's what this integral is doing. dx and dy are these little blocks, and this is the height of the blocks. So to do this integral, it turns out it's very convenient to change coordinates. And instead of using x and y, we're going to use what's called polar coordinates, where you have r and theta, where r is how far out you are, and theta is how around you are. And this makes sense because this is a spherically symmetric problem. Okay. And so what that means is instead of building up the blocks like this, I'm going to take the blocks to have this kind of form. Again, excuse my artistic inability. But the idea is we're going to take the same surface, but break it up in a different way. Okay? And so when you do that, there's a certain rule that tells you how to rewrite this thing. And so instead of doing x and y, we have r dr d theta, and then this is just r squared. Okay? It turns out when you change variables in the integral, that's what you get. You can believe me. Now, it turns out now that because there's an r there, and it's a function of r here, this is an integral that actually you do know how to do, okay? Because this, well, why didn't I even write it down? Firstly, the theta becomes totally trivial because there are no thetas here, so we take the theta out. In fact, that gives you 2 pi, right, as you integrate around. And here we have integral of dr of r e to the r squared, which is actually, okay, why didn't I go the whole way? That's actually a derivative of, it's a derivative of e to the minus r squared over 2. And if you remember any calculus, the integral of the derivative is just a function itself. Okay, and this is from 0 doing the whole plane. So anyway, this thing ends up being pi. Okay, so the point is that by changing variables, so the building blocks, the equivalent thing to the phonons would be these little regions, and we've changed the same problem to think of it in terms of different building blocks. Okay, and then the calculation we had to do, which is what physics is, okay, it's a calculation, becomes easier. Now, why is this relevant? This is not even an analogy. This is how it is, because it turns out that physics is one big integral. Okay, there's something called the path integral. So again, this is a change of, right, again, so the flip, there's nothing more fundamental with these little squares or these little wedges, okay? They're just 2 different variables. So similarly, it turns out that physics, there's something called the path integral that was invented by Feynman. And he says, what it says is that the way to do physics is that everything that could possibly happen happens with a certain probability, and you sum over all the possible possibilities weighted in a certain way. Okay? And so it turns out that according to this physics, okay, all of anything is one huge integral where what you might integrate over would be all gluons and quarks, for example. All possible with some weighting, okay, some function. Okay, so you think of all possible places you could put all the gluons and all the quarks. You sum them all up with weighted in a certain way. And from that, you can derive all the physics. Okay, that's what the path integral says. But you can do a change of variables of this integral entirely analogous to that, where instead of integrating over all the positions of all the gluons and quarks, you integrate over all the possible flux tubes. And then you'll get some different function, g here. And sometimes, if this function is easier than that, simpler than this one, then this is the right duality frame, as we would say. These are the right variables. So I haven't really, give me an outline here, but the idea is that this switch from gluons to flux tubes is a change of variables just like that is. Okay, that's what a duality is a change of variables. And if you were very fond of your pet, you could say, you could also rewrite it as a sum of all possible cats. Okay, everywhere a cat could be. That's also an equally good description of physics, but I can guarantee you that this function will be extremely complicated in that case. All right? So we never use that duality frame. All right? So, but in this way of thinking about it, there's no fundamental description of physics. Okay? You have many, many different choices of variables, and depending on what question you want to ask, a certain set of variables is more convenient than other ones. And so often, the smaller constituents are simpler, and we should write our equations in terms of the little things that things are made out of, but sometimes they're not. Okay? And then duality is we remind ourselves that we don't have to stay where we started. We might have made it. Look, gluons and quarks, again, were invented by analogy with electrons and photons. That doesn't mean that that's the right way of thinking about this problem. Okay? All right, end of calculus. But that's the idea of a duality, okay? That you don't have to stay with what you're given. If you're clever or lucky, you might find a different description. Actually, this would be a good. If there are any questions, this would be a good time.
Did you intentionally use F for the gluons and G for the?
That was I didn't think about that. That's what I get for improvising this. Yeah. All right. Good. Yeah. Okay. So then, how are we doing for time? Not too bad. Okay, so what happened is that in 1997, an Argentinian physicist called Martesina proposed a duality in exactly this sense, okay, that there are two equivalent descriptions of the same system, and that it's basically between the two things that I had on the board at the beginning. So that there's a duality between black holes, so the dynamics of black hole horizons, and a particular quantum liquid. So not all quantum, so remember, quantum liquids are these complicated things that are not ordered or disordered. So there are many of them. High temperature superconductors might be one. Various other materials are turbulent rivers are another one. Not quantum, just liquid. So a particular quantum liquid. So this particular quantum liquid, we're not going to talk about it that much, but just so you know, it has a fancy name. It's called N=4 super Yang-Mills theory. Okay. Just so you've heard the name. We're not going to. Now, that doesn't mean, so this duality doesn't let us solve all strongly coupled, all quantum liquids, but it says that there's at least one that we can get a handle on, okay? Because this dynamics of black holes, black holes might seem exotic, but it turns out this is relatively doable, okay? It just involves classical equations as Einstein wrote them down in 1915, okay? We just have to throw things into black holes and perturb the space-time and see how it behaves. Something that astrophysicists have been doing for 40 or 50 years, okay? So there's a lot of mathematical techniques and ideas that we can use for this. Whilst these quantum liquids, they're very difficult to describe. And so just having one example is like, this, it's a lamp. It's a lamp, a street lamp in a dark street. So the idea is to take a particular, we're going to call it a toy model, right? It's an example of something we can solve and see what we can learn from it using this duality, okay? So this duality tells us that to study this particular, so this is a particular medium, okay? It doesn't, doesn't matter too much about the details. But all of these ripples of black holes that we were talking about, it turns out that every question, so they seem like a mathematical artifact, as I was saying before. What is actually rippling, okay? I said it's just empty space, right? With space-time, bending a little bit, but there's no medium here, okay? And indeed, as you said, if you fall through the black hole, you won't see stuff, right? Probably. And this sort of resolves that, is that all these equations that look like they wanted to describe a fluid, but there was just no fluid there, okay, the reason it's doing it is because it's a dual description, okay? So when you calculate the entropy or the diffusivity or the conductivity of these black holes, what you're secretly doing is calculating the diffusivity, the entropy, and all the properties of this dual quantum liquid, okay? So I'm not going to explain this duality more than that, but hopefully from last time we saw that black holes did have these thermodynamic properties, and so all I'm telling you is, in fact, they are the thermodynamic properties of something, okay? So the natural question, I told you that one of the most interesting quantum liquids are the high temperature superconductors, okay? So now here we have a model, a system of a quantum liquid that we have a hope of actually being able to understand. So now we get to pick questions that we ask, okay? We can ask all kinds of questions. So what is the conductivity of this quantum liquid? Well, we know the answer is the conductivity of the black hole. But another interesting question is, can this quantum liquid become superconducting? Okay, because high temperature superconductors, the most interesting thing they do is become superconducting at quite a high temperature. So now that we have a solvable model, let's pick. So since 97, people have been asking all kinds of questions. And the one that I want to talk about today is, okay, so we have one quantum liquid we can understand. Does it become superconducting? So one question. Does the quantum liquid described by this duality become superconducting at low temperatures? Okay. And so what the duality maps that question into is, does the black hole become superconducting at low temperatures? Okay, it's the same question. Right. So let's now go back to our black holes that we talked about last time, and let's think, as we lower the temperature, remember the temperature was this surface gravity. It's a certain property of the black hole that we can change, right? If we make the black hole bigger or smaller, we'll change the temperature. Let's make it very small. Does it have something? Does it become superconducting? Okay. And if it does, then we've learned something about at least one quantum liquid, and that might help us understand things like high temperature superconductors. Yeah? Okay, so black holes. Can black holes become superconducting? So we're going to have to go on a few detours again, and I have to tell you what superconductivity is, which we didn't really talk about yet. So firstly, how in principle, how could a black hole become superconducting? So remember last time we talked about the conductivity of black holes, right? We said, okay, you've got your black hole sitting here. It's black. And we sat outside with a battery. Forget the observer. We had a battery, and we dangled some leads into the black hole, okay? And we'll see a current will go around this loop, and there'll be a certain resistivity, okay? There'll be a certain resistivity. In particular, as you drive the current through the black hole will get a bit bigger, which means it's generating entropy, and that's what resistivity does. It's the loss of, you're trying to do something useful, right? Move the charge from A to B, but when you do that, you find out you do some useless stuff, you generate heat, and that's the entropy, okay? So the black hole gets a bit bigger. So how could we do this setup without the black hole getting bigger, right? That means we'll have a superconductor, something that carries current without generating any entropy. Yeah, that's what we'd like to do. So the resistivity is the same as saying the resistivity is 0. So what needs to happen is that this black hole will need to get coated in sort of a sugar coat of what's called a superconducting condensate. So what's going to need to happen is that this black hole, the horizon of the black hole is going to have to get coated. We'll talk about this more. So this is the black hole. So if it's going to have to be coated sort of enshrouded in a superconducting condensate, which I'll also talk about. Now, basically with a sort of superconducting fluid, if you like. And what will now happen, we're going to spend a lot of time talking about this, that when you put this battery to the black hole and try to run the current, actually it doesn't go into the black hole, but the black hole gets short-circuited and the current just zooms along the superconducting coat. Okay, so we try to drive the current through the black hole, but it just shoots along this sort of layer outside it. All right. So now this then becomes the question: can you sugarcoat a black hole? All right? Can you do this? And in fact, this is the sort of thing that relativists have been thinking about since the 60s. And what existed were all kinds of theorems saying that this could not happen. Okay, so let's talk about these. Okay, so can this happen? So, yes.
When you say condensate, are you talking about material or space?
I will talk more about this condensate in a minute, but it's more like it's a material. It's really it's a misleading image that comes to mind, but it's a substance. How about it? It's something. Yeah, it's not just space. It's more than just space and gravity.
Does that mean that somebody falling into the black hole would taste the sugar?
What's that? Will taste the sugar? Yes, definitely, definitely. Yes. That's right. Yes, it's really there. Yeah. That's funny. Seem to be missing a page. Well, all right. So the. Okay, so I can either tell you what a condensate is, or I can tell you first why it can't happen. So let me start briefly by saying why people said it couldn't happen. So going back to black holes have various what are called no-hair theorems. So since the 60s until today, various no-hair theorems were proved. So this turn of phrase came from Wheeler, in fact. In the 70s, I think, he made up the phrase. So these no-hair theorems, which are a whole bunch, basically say that you can't put things on black holes. Okay, and this is a very good reason for that, which is that they want to fall in. Okay, you try to sugarcoat something on a black hole, it's just gonna fall in. So it's saying you can't put stuff, anything really, just outside a black hole. And it's really the stupid thing that it wants to fall in, right?
Is that the equivalent of no drama, of there being?
No, I think it's a logically different statement. Yeah, this is something that's sort of, although you can think of it of what you'd see if you fell in, this is mainly a statement about what someone outside the black hole would see. So I try to very gently drop some stuff into the black hole and hope that it just stays outside, and it's just not going to happen. And if you did, so it's a different, it's basically a different thing. And actually, even if it didn't want to fall in, there's something else that can happen, which is it can just radiate off to infinity. Okay, so actually, what will typically happen, it will fall in, or if we try to do something clever like maybe having it spinning around the black just on the horizon or something, or it radiates off to infinity. So infinity just means a long way away, right? In fact, so typically what will happen is that you try to put it outside, it'll fall in, space-time will wiggle a little bit, and there'll be some gravitational waves going out to infinity. So some stuff will go out to infinity, some stuff will fall into the black hole, but nothing will stay outside. And it was proven, the theorem, it's an honest theorem, that you can't do it. Okay. So we'll come back. Let's keep you I'm not going to answer this yet, so we're going to come back later and see that there are loopholes, there are ways around this. But first, let me tell you a bit about now what's the thing that we want to put outside the black hole, which is this condensate. Okay? And this amounts to explaining what is a superconducting condensate. Now, it turns out that that's actually a bit difficult to explain. And I spent a lot of time last night looking on the internet, surely other people, people have tried to explain superconductivity. And in fact, the explanations are just universally wrong. And I don't mean this in a pedantic scientist kind of, the details weren't quite right. I mean, they're just made up. They're not related to reality. And there's a good reason for that, which is it is quite difficult. So I'm going to try not to lie. I mean, I've told a lot of little lies, but I don't want to tell any, deep lies. But that means that this description is not going to be totally complete. Okay, but so let's try. It's just one of these things. It's very quantum mechanical and mathematical, and it's not easy to explain. But let's see what we can do. So I want to try to explain what a superconducting condensate is. Okay. So it has two parts, and it's the first bit that I'm not going to explain that much. And the first bit, I'll do an analogy. So you all know that the Higgs boson was discovered relatively recently, right, in this particle accelerator. And I'm sure you've all heard the phrase that the Higgs boson gives particles a mass. Okay, that's the one thing, the catch line. Now, most of the explanations for that are also pretty misleading. And it's difficult, in fact, so they say the Higgs boson is like treacle and that you move through treacle, and that's difficult. That's actually pretty misleading. But I'm just going to get out by saying, so the first thing that superconducting condensate is that it's like the Higgs boson. So the Higgs boson is also a condensate. Okay, it's something. So a condensate is something that's permeating all of space. Okay, it's everywhere. It has the unusual property. So normally, if I have a solid medium here and I run at it, I'll hit it and that'll hurt. But the Higgs boson, if you run at it, it looks the same. Okay, so it's a little. Okay, but it's a kind of medium. Okay, so like the Higgs boson, so it's a medium. Throughout space. Although actually in this case, I'm not going to want it to be everywhere in space, but just outside the black hole. Okay, it's a medium. And it has the property, like the Higgs boson, that when certain particles move through this medium, they acquire a mass that they didn't have before. Okay, and so certain particles in this medium. I'm going to have to tell you what a mass is too, because it might not be quite what we think it is. So certain particles in this medium acquire a mass. Now, the difference between the condensate in a super. So in fact, some of you may have heard that the idea of the Higgs mechanism actually has a precursor in superconductors. It was actually discovered first. I mean, essentially in the context of superconductivity. Okay, so a superconductor is a Higgs mechanism, so it's this condensate that forms, but the difference is that different particles get a mass. Okay, so the Higgs boson gives a mass to protons. Gives a mass to electrons and various other particles. The superconducting condensate, the thing it gives a mass to is the photon. Okay, so. In particular, so in a Higgs condensate, so that's the one from particle physics. The things that acquire a mass are things like the electron, the Higgs particle itself, W bosons, all kinds of various particles acquire a mass. Okay. In a superconducting condensate, what gets a mass is the photon. Okay. So firstly, I'm going to tell you what that means, that the photon gets a mass. And secondly, I'm going to try to argue that when the photon gets a mass, that's equivalent to superconductivity. Okay? So these are the two steps. So I didn't really explain how the Higgs mechanism worked, but I told you that superconductor is like the Higgs mechanism. So whatever explanation you read in the New York Times or somewhere for the Higgs mechanism also applies for superconductors, okay? Or doesn't. Yes, okay. All right. I'll work on it, and let's see if at some point in the future I find an explanation. All right, so what does it mean that the photon becomes massive? So let's talk about the consequences of the photon becoming massive. All right. So what did the photon do? Remember that I told you before that what the photon did was mediate the force between two charges, right? So if I had a charge here and a charge there, then they would exchange photons. And this exchange would lead to a force that went like 1 over r squared. Okay? So one thing that happens when the photon gets a mass is that it doesn't travel so efficiently between these two charges. And so the force, we call this as an example of screening. Yeah. The force, so this is with no mass. So the photon doesn't normally have a mass. But when it's going through a superconducting condensate, it does have a mass. And the force now goes like, the 1 over r squared is still there, but now there's an exponential, e to the minus the mass times r. Okay, so that means that, let's just draw, if these formally don't mean anything to you, we can just draw them. So before we had a particle there and a particle here, and the force between them, well, the sign doesn't matter too much, fell off like 1 over r squared. Okay, so this is 1 over r squared. So as you get further away, the force gets weaker in this way. This is an exponential fall off. Okay, that means that now it looks more like that. All right. So once I get further away than a distance that's 1 over the mass, then basically I just don't even see the other. This charge doesn't even see the other one because the force has fallen off so quickly. So it's like it's not even there. Okay. Another way of saying that is Gauss's law doesn't hold anymore, if that means anything to you. And in fact, another way of saying that, and this is equivalent to saying that basically the photons don't enter the superconducting region. All right? So they travel. Sorry, is there a question? Yes.
Are these photons that you talk about going back and forth, like, I mean, are they like honest to goodness black bulb photons, or are they more like virtual accounting type photons?
Well, they can. It depends what you want to. This happens to both of them. So in terms of this force, you would probably think of them as virtual photons. But it's also true that if I, just try to apply an electric field, which is made out of photons, that the electric field just won't penetrate this medium. It'll sort of mostly go around it. So it applies in both cases. Okay, so here's my attempt to, I think is true in essence, to explain superconductivity from this fact. Okay. So what's the conductivity? So the conductivity, you apply an electric field, right? You've got your sample, you apply an electric field, and that creates a current, right? The electrons start moving, right? That's what a battery does, right? It applies an electric field around your current, around your circuit. So, and the conductivity is defined as the constant of proportionality, right? So you apply an electric field, the more current you get, the better a conductor it is, right? And that's the conductivity. If you want so in a superconductor, the conductivity is infinite. The resistivity is basically 1 over the conductivity. Okay. So, but this is a more useful concept here, right? So again, you've got your medium, you put a battery around it. That means you're applying an electric field, and you like the charges to move, right? And that's a current, all right? And so how well they move is measured by this conductivity. That's what this formula says. And in a superconductor, they move perfectly, that means the conductivity is infinite, all right? Or the resistivity is 0 in a superconductor. So now let's imagine that we've got some material, and let's say we make it superconducting in a little region here, and then the material continues, okay? So here it's superconducting. Yeah, I mean, this is a little formal, but I think it is the essence of it. So now, let's say we set up a state. I apply an electric field, and that'll set the charges moving. So sorry, there's a wire that goes through. So I send the charges going along the wire. Now, charge is conserved, okay? So whatever goes in there has to come out there, right? So that means that the current is going through. There's a uniform current J along this wire, okay? But the electric field, what happens because of the mass is that it doesn't go into this medium anymore, okay? As soon as it tries to go into this medium, it travels very badly because of this mass, right? This mass is telling you that the photons, you send out these photons, but they don't go very far. And the electric field is just made out of photons. So roughly what's happening is that the electric field is basically 0 in here. But the current is not 0 because the current just keeps going, okay? So in here, you have a current without an electric field. And the only way that can happen is if the conductivity is infinite, okay? Right, so in here, there's no electric field, but there is a current, and actually that's telling you that the conductivity is infinite. Right. And so it's a superconductor. So that's a little slick, okay, but I think it's broadly true. But the main point that I want you to take home is that there's something like the Higgs mechanism. A superconductor is like the Higgs mechanism in particle physics, but what gets a mass is the photon. That changes the behavior of electric fields, and it's that fact that can make things be superconducting, okay? Although I haven't probably really explained it very compellingly, okay? Yes?
So it's not electrical field going away that causes the magnetic fields to be.
Yeah, so it turns out magnetic fields also can't get into this superconductor. And in fact, yeah, there's some things that are not totally satisfactory about what I'm saying, but let's leave it at that. So it's normally considered the more fundamental fact that magnetic fields can't go into a superconductor. Okay, so again, let me just repeat that. So a condensate is a sort of medium that can form, and when you have a condensate, certain particles become massive, which means they don't like to travel in that medium. And for a superconducting condensate, what happens is the photon becomes massive, okay? And that means an electric and magnetic fields can't make it into the medium. And it turns out that that causes superconductivity. And the argument is something like that. All right. Any questions? Yeah.
How thick is the coating?
How what, sir?
How thick is the coating?
Is the what?
The coating.
Oh, the coating. Yeah, okay. So no, we're coming back to black holes now. So we're coming right back. So that what I told you, that's all 3 minutes and we'll get there. So this was just an interlude about condensates in general. And so when you get a superconductor, in niobium or whatever your favorite superconductor is, that this is what's happening. But now let's go back to the black holes. Okay. So at the moment, there's no coating because it didn't exist. So the black holes that appear in Maldaceno's duality, the ones that we're going to care about at least, are different from astrophysical black holes in two important ways. Okay, so all these no-hair theorems apply to black holes, in the sky or in the center of the galaxy. So they're different in two, well, actually many, but two important ways. one of which I mentioned last time and one of which I didn't. So I mentioned last time that to really study black holes have this annoying feature that they want to radiate away and just collapse and collapse to zero. Okay, that makes them very hard to study because they're inherently unstable. And so in this duality, the way you get around that, as I mentioned last time, is that you take your black hole and you put it in a box. I think I had a square box. It doesn't matter. And you heat this box up with a candle, and you heat this box to the Hawking temperature of the black hole so that they're in thermal equilibrium and the black hole doesn't radiate and evaporate. So you have to put the black hole in this sort of perfectly reflecting heated box, okay, theoretically, right? So this box stops any radiation going out to infinity. It sends it back in. Okay, so this box prevents things radiating out to infinity. Okay, so that was one part of the problem. Okay, we sort of just solved it by fiat. Okay, we put the thing in a reflecting box, so stuff can't. So anything that tries to radiate away, it bounces back. All right. But the more interesting part is that it turns out the black holes that we care about for these kind of questions are not neutral black holes, but they're charged. So let me tell you a bit about charged black holes. So by charged, I mean that we've got our black hole sitting there in the middle of our box, but it carries a net charge. So that means that there's an electric field shooting out of this black hole in all directions. Okay, it's an electric field. And so what that tells us is that there must be some charge in the black hole. We have no idea what it is that's carrying the charge. Okay, it's electrons or charged cats or whatever. So because that's the entropy, we don't know what's making up the black hole. But the fact that it's charged, we can know. So when I say coming out, you shouldn't think of it that in time something is coming out of the black hole. It's just that it has the property that if you sit some distance, if you put a charge here, so let's say the black hole is positively charged, then a positive charge will get pushed away. So you can have a black hole with charge coming out of it. So why doesn't this exist in astrophysics in the sky? If such a thing did exist in the sky, then immediately all the negatively charged particles that existed outside would get sucked in, and they would neutralize it. Okay, so right, if you've got this charge, positive charge attracts a negative charge will all just fall into the black hole, and it'll want to neutralize. Okay, so unless, right, okay, so that's why it doesn't exist in the sky, but in our sort of theoretical universe, it can exist as long as there are no extra charges around.
Excuse me,
Yes.
how can you exchange radiation between your inside and your outside?
Yes, so these you probably more want to think of in terms of virtual. These you probably are not dynamical photons that are traveling. These are more like someone mentioned these. Yeah, actually, yeah, it is a bit tricky to explain.
Why don't you say it's electric field?
Yes, but if I said they're made out of photons, why don't the photons in the electric field fall into the black hole? Yeah, it's a bit tricky. But yes, let's think of it not as a thing, but as an electric field. But I think maybe the best way to think about it is in terms of not real photons, but these virtual photons that can get exchanged between things. And then something outside the black hole can feel the electric presence of something inside the black hole, even though it doesn't know what it is. But that's actually, it's a pretty subtle point. It's a good question, and I haven't really answered it. Good. So now, okay, but so the idea is, yeah, you've got a black hole, and there are electric field lines coming out of it, okay? They're not, again, it's like, so if it was magnetic charge, and you had your iron filings, you just see iron filings coming out, following these lines out of the black hole. It's not that photons are popping out of the black hole, right? It's just the field. Right. So now, I said negative charges will get pulled in, but positive ones will get pushed away, okay? And then that now gives us the chance that maybe we can sort of put a halo of positive charge outside the black hole where the electromagnetic force stops it, beats the gravity and stops it from falling in. And so the idea that we're going to pursue is that we're going to put some charged hair on this black hole, okay? We're going to put some stuff, a charged condensate outside the black hole that's not going to fall in because it's repelled by the charge of the black hole, okay? So we're enlisting another force of nature, electromagnetism, to combat gravity, okay? So so how does this work in practice? And so how big the halo is going to depend on how much gravity is pulling it in versus how much it's getting pushed out. So we'll see this in a minute. So let's see how this works. Okay, so here's how it works. So by it, I mean putting something outside the black hole. Okay, very good. So what's that picture? We've got our black hole. It's in a big box, and it has electric field lines coming out of it. All right? That means electric field. All right. So we need one more little thing. So it turns out that whenever you have electric fields, something that can happen is something called Schwinger pair production. So I think this will be almost the last concept. So whenever you have an electric field, because that was our setup, right? We started, this was our dual description of a quantum liquid, okay? It's this electrically charged black hole in a box, right? That's our object. So whenever you have an electric field, something that can happen is something called Schwinger pair production. And this is when a particle and an antiparticle pop out of the vacuum. Okay, so let's draw that. So let's say we had a positive charge here and a negative charge here. Then we've got some field lines, some electric field. Of course, also floppy, but there's some electric field going from one to the other. So Schwinger pair production is a process in which you still have these charges, you still have some electric field going from one to the other, but now you pop out of nowhere an extra negative charge and an extra positive charge, and these have a field going the other direction, okay, that partially opposes the first one. So why can this happen? So some famous physicist, I forget who, said that a useful principle is that anything that can happen does happen, okay? And so let's see why can this happen, okay? So one thing that had better be conserved is energy, okay? And so by creating two new particles, you've increased the energy because every particle has an mc squared energy, right? So let's do our energy bill. Let's balance the energy. So here there's some more energy because we created two new particles. Let's say they have the same mass. So there's an increase in energy, which is 2 times mc squared, right? Where that's the rest mass energy of these two particles. However, because these particles have created an electric field that opposes the one that we started with, in this bit between the particles, there's less electric field than there was here, right? Because it's canceling out. And it turns out the electric field is a type of potential energy, right? Remember we said that a particle on top of a hill has a lot of potential energy. That's because it's in that's the potential energy of the gravitational field. So similarly, an electric field has potential energy, and because we've reduced the electric field, we've reduced the potential energy here too. So there's another change of energy, which is minus, so there's a loss of, by this I mean the potential energy has gone down because we've reduced the electric field. So that's why when I say this process is allowed, and we can just add two particles for free, because if they have an opposing electric field, they can steal the energy, they take the energy from the electric field and use it to create this pair of particles. That's a way you'll see this described, right? Is that it's a process where potential energy is converted into rest mass energy of these particles. Okay, so it's a process that preserves energy, and so in principle it's allowed and it happens. Okay. So eventually, of course, these particles will keep getting produced, and eventually there'll be no electric field left. Okay, more or less. Okay, so that's the idea. So by the way, this notion, this is a very, we're going to come back to it, a very, very important concept in physics, which is called screening. Right? That we apply an electric field to a medium, and it's going to do whatever it can to cancel it out. Right? We'll create new particles to try to create an electric field that cancels the one that we added. All right? Good. We're going to come more screening. Yeah, this makes sense? So actually, if you take one concept away from today, it's a little tangential, but the screening and anti-screening, I think, are really, really important concepts. I'll come to anti-screening in a second. Okay, so what happens if Schwinger pair production starts happening outside the black hole? So we have our black hole, has its electric field. And now what happens, so let's say the black hole is positively charged. What happens if a negative charge and a positive charge pop into existence outside the black hole? Right? Well, they feel some competing influences, right? So both particles have mass. Okay, so according to their mass, they're going to be attracted to the black hole, which also has mass. So masses always attract. So both of them want to fall into the black hole. But according to electromagnetism, to electrostatics, the negative one gets attracted in, but the positive one gets pushed out. Okay? And so, yeah, let me mention again. So this is screening. So from the electric point of view, they want to screen. Okay, meaning to screen the field, the electric field, right? Meaning that the minus one wants to fall in, the plus one wants to go out, and that'll reduce the field. But by gravity, they want to anti-screen the field, which means they both want to fall into the black hole, and that'll make the black hole even bigger, and it makes the field bigger. Okay, so gravity is inherently unstable, right? If you have a gravitational field and there's some stuff here, it all gets sucked into that field, and the field just gets bigger. And on a tangential note, that's where all the matter in the universe comes from. The galaxies in the universe come from, right? So the universe started out, more or less homogeneous, but all it takes is a very little bump in some point in the universe and a few billion years, and everything it clumps, right? Because the more stuff it gets, the stronger it clumps, right? That's the opposite of electromagnetism. That electromagnetism is very modest. It wants to cancel itself out. Okay. So what's happening to this pair of particles that appear outside the black hole is that there's a tug of war, right? The gravity wants black hole. The gravitational aspect of the black hole wants to be bigger, but the charge of the black hole wants to reduce itself. Okay. And so this is where the temperature comes in. So for these black holes in boxes, it turns out the higher the temperature, the bigger the black hole. This is not the same as astrophysical black holes, which you might have heard of. So very good. So it's about electromagnetism versus gravity. Okay. So if the black hole is big, let's fix the charge of the black hole and imagine changing its size. When the black hole is big, for these black holes in boxes, it turns out this is the same as saying there's a high temperature. Okay, I remember I told you that the temperature of a black hole was related to its surface gravity. Okay, I told this last time. And it turns out for these black holes I'm talking about, when they're big, it's a high temperature. In this case, gravity wins, because it's just the black hole has more mass. It's big, all right? And that means these pair-produced particles, they don't do very much. They just fall into the black hole, and everything stays more or less the same. So the black hole gets a bit bigger. Okay, now let's do the other. But if the black hole is small, which is low temperatures, then the electromagnetic force wins. Okay? Well, then what happens? So then the negative charge falls into the black hole. So the black hole had a bunch of charge. So the charge gets a bit smaller because the negative charge fell in. But the positive one just sits outside the black hole. Okay? It's not going to fall in because it's repelled. And its gravity is not strong enough to make it pull in. And also, it can't get pushed away to infinity because there's this box that we put the black hole in. And so when this process keeps happening over and over again, what you end up with is a black hole that's somewhat less charged, and then there's a little condensate of charge sitting outside the black hole. Okay, and this condensate of charge is what causes, it gives a mass to the photon and causes superconductivity. So this is the superconducting layer. Outside the black hole. Layer, or we could call it hair. Outside the black hole, okay? And so that's nice. So just to, we're coming very close to the end here. So we've indeed found that as we lowered the black hole, as we lowered the temperature, the black hole becomes superconducting. Okay, so let's say we have temperature. That's our temperature axis. So this is high T. This is low temperatures. What happens is there'll be some critical temperature where the black hole is no longer heavy enough to swallow all these pair-produced particles. And instead, the positive one gets pushed out. And so that's our TC, our superconducting temperature. And below this temperature, it's superconducting. And above this temperature, it's the black hole, which is, if you like, the quantum liquid. Okay? So this dynamics is like, yeah, tell me.
So are you assuming a fixed amount of charge here? Because you keep referencing big, small temperature, and it seems like there should be a relationship to the size of the charge.
No, that's totally correct. So good. Yes, you're quite right. And so, yeah. So there's several details here, but that's an important one. So we have this black hole in a box, and what we're going to keep fixed is the total amount of flux going through this box. And by Gauss's law, that's equal to the total amount of charge in the system. So yeah, we keep the total charge fixed, if you like. Yes. The total charge as seen by someone very far away, which is they'll measure by how much electromagnetic field is coming towards them.
And if you change that charge in this box experiment, it would change what temperature and what size.
Wonderful. Exactly. So this TC, indeed. So TC is set by the total charge, indeed.
So in this type of setup, how is the black hole, the small black hole, different from any other type of charged body for our purposes? We are kind of
Good.
gravitation is small, charge is there.
Indeed. So in a way, well, okay. So actually what this actually mimics what happens is observed to happen in superconductors, which is that if you're at some temperature here, let's say, below Tc, but let's say not a zero temperature, but at some finite temperature, there's actually and you run a current, you actually see that there's two components. So there's some of the current is superconducting, and some of it isn't. So actually, actually that's a bit, okay. So there's still some black hole left, okay? Now for charge, that doesn't do anything because it always gets short-circuited by the superconducting bit. The charge always takes the path of least resistance, so the conductivity is infinite, okay? However, the black hole will still have some entropy, and you'll see that. So what I'm trying to say is when you're here, there's still some black hole left. And that will do things. So it's not, the black hole hasn't, there's a certain balance. Okay, there's sort of equilibrium point where the charge and the mass of the black hole balance themselves. So there's a black hole left, and that will certainly do things. I'm not sure that was your question.
I think the question was, what if you could replace the black hole by just a chunk of something else that also could have charge and also could...
Wonderful, wonderful. Yes, yes, good, good. Thank you. Sorry, gotcha. Great, thanks, Lenny. So this story is not so different. So you could have a lump of metal, a star surrounded by a superconducting halo. That could totally happen. But what you won't have is this quantum liquid out of which it's born. So the fact that here, by solving classical equations, you can get entropy and diffusion of charge and so on, that won't happen for a star. That needs a black hole. So this duality. So okay, what was our objective? One of our objectives was to start to understand high temperature superconductors, in which superconductivity emerges from a quantum liquid. So the black hole is the quantum liquid. If you take away the black hole, you won't get the quantum liquid anymore. And so that's right. Yeah. But a star could very well have a superconducting condensate outside it. Yeah, definitely.
To clarify terminology used earlier, I think you said in 97 Montesina proposed this duality. Is it considered mathematically proven, or?
Okay, so proven that we can take to the bank, no. But so there have been over 10,000 papers written. Touche, yes. Okay, but there have been thousands of papers written based on this duality, and no inconsistency has appeared. So it is true. It is true. Yeah.
I got slightly backwards. Is the low temperature regime there equivalent to a gas because it's disorganized because things flow freely and without constraint, or is it, or you can't even talk about
that? It's subtle, but yes, the superconducting state. For example, let's say if these high temperature superconductors, they behave very strangely above TC, but once they become superconducting, they become much more normal, in fact. And so this is
solid versus
gas. Well, actually, it's a bit of both. It's a bit, but not in a complicated way.
And then the high T regime beyond quantum liquid is what?
Here, you mean?
Yeah, above.
Oh no, this goes all the way up.
But what is that? What is the equivalent state? You're not even discussing.
So what do you mean? What's it?
Solid versus
It's like a liquid.
gas versus.
It's liquid. This is the quant. Yes, yes, yes. It basically goes all the way up until the thing melts, and then when it melts, you don't have it anymore. So yes, it's a quantum liquid. So it's very complicated. Yeah, let's leave it at that. But the superconducting state is more normal. It's more like a gas.
Does it say how high TC can go? Will you get room temperature superconductors?
Good. So, there's this very bad joke about, if you want to find room temperature superconductivity, we should all move to Alaska. But well, actually, good. That's what, yes and no. So in this set of, sorry?
In German, they call it Jein.
Jein. Okay. Yes, exactly. Good. So in this framework, in this toy model, there is a formula for TC, and it depends on the charge. So in principle, if you were to increase the amount of electrons in the metal, which is what this charge is, that's this doping. Remember I talked about doping last time? This would predict that TC would be proportional to this doping, which in principle could be arbitrarily large. Now, in a real metal, there's all kinds of things like disorder and lattices, and things break if you try to push them too much in one direction or another. So this is, and also this is a toy system. This is not something you can go build tomorrow. Maybe, people, one of the interesting developments of physics in the last few years is that people are starting to engineer quantum mechanical systems better and better using cold atomic lattices. And so maybe in 100 years, we'll be able to design n equals 4 super Young mills, and then this will happen. But at the moment, it's a theoretical system, right? But it suggests that TC can be high. So for a conventional superconductor, there's something called BCS theory of the Bardeen, Cooper, and Schrieffer that describes how, let's say, niobium becomes superconducting. And that there's a formula, Tc equals something called the Debye scale, okay? And then there's an e to the minus 1 over lambda, where lambda is a very small number. So what this factor tends to do, you have a natural scale in the problem, but it turns out that the dynamics wants to make Tc be much lower than that scale. Maybe one lesson that we have from here is that there's a natural scale, which is the charge in this case, but there's an order 1 number. It's not much smaller. And so this is sort of an artifact of the fact that the normal state is more sort of like a gas. And here we see that one thing that we could try to learn in quantum liquids is that you're not going to have these suppression factors typically. Okay, so whatever the natural scale in the problem is, in this case the charge, Tc is going to be set by that scale. But as always, the transition from theory to actual materials is a tricky one.
I heard there are other phases, like Sugar gap phases. Are they also distinguishable in black holes?
So good. So what this question is saying is that, so you know I drew this phase diagram of high temperature superconductors last time, where this was temperature and this was doping. And there was this region that was superconducting. And remember there was this region here that I said was a Mott antiferromagnet. Okay, so very ordered, very rigid. And then there was a sort of normal metal over here. And everything I've been talking about is this quantum liquid, which is sort of this area in the middle. Okay. It turns out it doesn't end there, and there's a mysterious region here that's called the pseudo gap. Okay. And so when something's called a pseudo gap, it's because it's like a gap, but it isn't. I haven't told you what a gap is, but it's also not understood. So yeah, yes, definitely you can start to think about that in terms of black holes. Yes. But yes. The short answer is yes.
I was wondering if there can be an overlap between the so-called high temperature mechanism and the conventional superconductor. Like you can find
the high temperature what's it?
High temperature superconductivity and conventional. Or could you find two?
An overlap? Yeah, well, that's a good question actually, because so you see that here, there's this dome, and the superconductivity is getting lower down here, and so you might ask, well, is this superconductivity here that's sort of closer to the normal metal? Maybe this has a more or less conventional explanation, and this one doesn't, and maybe they are continuously connected in some way. Okay, not known. So in fact, good. So here's the phase diagram, and the bit that everyone wants to understand is this bit. All right, why is the Tc high? And so what's your options? So you have to go to some limit that you understand, right? So half the papers are written, they start here where they know what's happening. This would be close to your question, and they think they know what's happening there, and they try to move in. And eventually the description doesn't work anymore, but they use it anyway. Or you can start on these mod insulators, which are also well understood because they're ordered, and move in that way. And this talk has been going down like that, right? That we're trying to say, let's get a handle on this quantum liquid via this duality and then see where superconductivity comes from there. But there are many sort of inroads into this phase diagram, and hopefully they'll all meet in the middle. Okay, so I just wanted to say, actually, we are basically done. So I wanted to say, just the last thing. Okay, so so we've gone from black holes to superconductors. Okay, so charged black holes in a box. When you cool them down, you start producing particles and antiparticles, and if the black hole is cold enough and not heavy, then that tends to discharge the black hole, and you get this condensate outside. And it turns out that via this duality, that corresponds to a transition from a quantum liquid to a superconductor, which is something that's of relevance in the real world. Okay, so what? So then work in progress. So this has led to a lot of questions, and so I just wanted to mention the sort of things you can now try to ask. So this is a mechanism for superconductivity. Okay, so in a conventional superconductor, you might have this BCS theory is all about the lattice vibrations interacting with the electrons in a particular way that makes it superconducting. That's a mechanism. This is a totally different mechanism that to understand, you have to go to this dual picture using black holes, and it seems somewhat exotic. But we can ask, so does this mechanism, and so mechanism literally means find the dual theory, understand Schwinger pair production in the dual theory, and derive Tc. So does this mechanism have clean experimental consequences? Or signatures, let's say? The short answer is yes, but we're not going to have time to talk about them. And then also a question but that's sort of under investigation. And another question that indeed came up is, it's the million-dollar question: what sets TC? Okay, can we learn anything about what sets the superconducting temperature in a quantum liquid? Okay, and so we have a playground now. We have a theoretical model for the kind of systems we're interested in, and so now the question is to sort of calculate as many things as we can and try to get a picture of what's going on, to see to what extent we can make contact with this real-world phase diagram that's not very well understood. Okay, yeah, so I'll end there. Thanks. So, the questions? There was a question over there somewhere. Yes.
Is it okay for the virtual photons to have mass? Do they become real once they get mass? And how that plays into this here?
So whether they have a mass and whether they're real or not are both fine. So is that correct? Yes. So they all get a mass. So right, exactly. So good. This question came up before, right? So this is the two aspects of this superconducting region, right? So you want to, on the one hand, if you have an electron here, and let's say a proton there, the force is mediated by virtual photons, and normally the force went like 1/r², but because of a mass, this became exponentially fast they fall off. So that's telling you that the mass is affecting the virtual photons, okay? But also the fact that you have a region that with this condensate that the electrons, the photons don't want to go into that medium. Those are real photons that are also experiencing the mass. So the condensate affects everything.
So using this duality, is there something that you can say about what is it that's special about this particular material that can be a high temperature superconductor? Like, what is the differentiation? How would you say this is likely to be a high temperature superconductor?
That's a very good question. So let's see, how should we go? So I think not that much, but maybe a little bit. So that's related to this question. But really, there are two steps to what you asked. So if you have a metal, for example, these copper oxides that make these high temperature superconductors, it's pretty complicated. I mean, the chemistry is pretty complicated. Okay, there's copper and oxygen and lanthanum and strontium arranged in a complicated way, and so there's some. But let's say there's some underlying lattice of copper and oxygen atoms. Okay, that's the chemistry of it. And then the electrons are going to hop around this lattice. Okay. And so question one related to what you asked, you could say, what will be the features of what chemical systems, what materials are likely to behave like quantum liquids? Okay, that's one question. And then another question is, once you've got a quantum liquid, what properties of it are going to determine at how high its superconducting temperature is? Okay, you probably don't want to go from there to there directly. Now, so this step, that's the step that this duality is going to help you with, in the sense that once you've got something that's behaving like a quantum liquid, you now have a model to how to think about it. Now, but this step, what systems become quantum liquids? Well, what we know is that they have to be between order and disorder, for example. So we have general ideas. So for example, in fact, this is very interesting. So normally, this was something that seemed paradoxical at first about these high temperature superconductors, which is that, so this was doping, remember, that was temperature. And so the chemical you're given is this undoped compound here, okay? That thing is both insulating, so if you get superconductivity, it's not even a metal, right? And furthermore, it was magnetic, okay, that the spins were organized, were flipped, right? So the conventional wisdom is magnetism and superconductivity don't go well together because, as I mentioned, when you have a superconductor, magnetic fields can't go into the superconductor. So these spins that create little magnetic fields, if there's a superconductor there, they can't do what they want to do. So they don't like superconductivity. So both because it's insulating and because it's magnetic, this seemed like the last place you'd want to look. It would have seemed 30 years ago like the last place you'd want to look for a good superconductor. However, in the view of the full phase diagram, where there's magnetism here but not over here, it is a good place to look for a quantum liquid because there's some order and then there's no order and there's a bit in the middle where it's a liquid. And so and then if it's true, if this step is true, the quantum liquids can generically lead to high TCs. Okay, that's the kind of question that this duality can address. Then suddenly these things with magnetism are good places to look for superconductivity, in fact, because the competition between different effects can lead you to these strange phases of matter where everything's interacting very strongly. So I'd say there's a set of intuitions for how to go from here to here that's not related to duality, and then there's this set that would be. That makes sense.
I have a question, John. If I have a real superconductor, I can do experiments on it that will tell me what charge of the fundamental charge carriers are.
Yes.
As you know, we'll find that it's 2, not 1. Yes. Because the charge is like a pair. What happens here?
Yeah, that's a very good. So yes. So let me repeat Lenny's question, and I'll say a few things about it.
Well, my question is, what are the charge carriers?
Yeah, I know it's a question. Yeah, okay, but let's. I think. Let's see. So in a conventional superconductor, you have electrons. Okay, and I didn't really talk about it through lack of time. But these things that form the condensate, they have to be both. So you might know that fundamental particles come in 2 types, bosons and fermions. And these condensates are made out of bosons, right? It was too tangential, so I didn't mention it. But the electrons are fermions, okay? And actually in a conventional superconductor, again, like I keep saying niobium, I'm not sure why, it has a relatively high TC for being a single element. Then you can, what happens is, I'm just going to mention these words. These electrons sort of bound together to form something called a Cooper pair, which is like a new sort of single particle, if you like. And this now has charge 2e. And the condensate is made out of these bosons with charge 2e. And you can measure this charge, actually. And so, in fact, it's very interesting. Before BCS theory, there was a theory of superconductivity by Landau and Ginzburg. And they wrote down some equations that were successful. And actually, Ginzburg, who was sort of the younger person in this collaboration, said Landau, Landau, because they didn't know about Cooper pairing. Okay, this was before BCS theory. And he says, our theory fits the data better if the charge carriers have charge 2, not 1. Okay, and then Landau said, no, that's ridiculous. How could they possibly have charge 2? Clearly, an electron has charge 1. And so they just ignored the data and they wrote down their theory, which was correct. But they assumed that the charge carriers had charge 1. And then a few years later, BCS had this theory of pairing that actually explained why it had charge 2e. Tangential comment. But so you can measure this. And so if you can measure the charge of the particle that's causing the condensate, then you have some insight into what the physics is. So indeed, in the Cooper, in these high temperature superconductors, this has been measured, and it is 2e. Okay, right, so in the high TC, the charge of the Cooper, the condensate is 2e. Yeah, I'm getting there. So in these quantum liquids, I think, but I'm actually not 100% sure, that you can in principle get anything. But I'm not sure. That would go into one of my questions, actually. So black holes can, in principle, allow for even more exotic forms of superconductivity, where the charge of the condensate could actually, I think, pretty much be anything, in fact. But, I mean, it could be 2e in particular. But I think...
But will it be quantized?
Yeah, I'm not sure. I'm not sure. is not obvious, actually. That's one of the questions that one want to think about.
Is there any relation between tenfold classification of superconductors based on absence or presence of various symmetries and black holes and this duality?
No, I think it's well, it's not that they're connected, but anything that's a classification, these will certainly fall in the classification somewhere.
I'm a little bit confused about the duality. The examples you used, there were two different bases or ways of calculating the same physics phenomena.
Yes.
Either using different, x, y equals r theta, or using quarks and gluons versus the flux. There were different methods of calculating the same phenomena. But in this black hole liquid thing, there's two different physical phenomena. We're using the same mathematics to calculate.
Good.
So it seems like it's a very different kind of duality.
No, so it is really the same, but it's true that so every single possible question you could ask about the quantum liquid has an analogous question. For every question you could ask in the quantum liquid, there exists a question in the black hole that when you ask it, you'll get the same answer. So they look very different, certainly, but that's because in any given regime of parameters, one description will be easy and one description will be difficult. And so, but there's a dictionary, the holographic dictionary, which says that, what I just said. So there is a precise, let's ask a question. So you say, what is the conductivity of this quantum liquid? Okay, that's a certain question. And to answer that question in the quantum liquid, you apply electric field and you see how much current moves. Okay, so then you have to go to the black hole side, and there's going to be a question whose answer is the same. Okay, and actually, just to give you a bit of a sense, what that question ends up being. Okay, so what was so duality? Every question you have to be able to ask every question on both sides because they're the same system secretly, right? So let's say you want to apply an electric field, and you want to see how much current is created. Okay, so applying electric fields is the same as a voltage difference, right? That's a battery. That's how you create a current. So in black holes, the way you do that is you take your box with a black hole in it, and you set up a voltage difference on the boundary of the box, or you apply an electric field this way on the boundary of the box. Okay, and so that means you have your space-time with a box in it, and over where the boundary, you set up a voltage difference. Okay, it turns out that what that will do is it'll send some photons rippling into the black hole. Some of the photons will fall into the black hole, and some of them will get bounced back, it turns out. How many fall into the black hole determines how much the black hole grows, which determines how much the entropy increases, which determines the resistivity. And so the answer to this question, which is the resistivity or the conductivity, also has an answer in the black hole duality frame, which is how big does the black hole get when you do a certain thing to the box. So there's this, okay, that's how it works.
Can you answer that just using general relativity?
Yes, of course. Coupled to electromagnetism. Yes.
Right. And not using anything about the microscopic structure of the conductor.
So, yeah, I mean, this is a more radical duality than these other ones I talked about, definitely. But it's really the statement that you could be living in this black hole in a box, or you could be living here, and you'd have different words for everything, and you'd have different ways of thinking about it, but it's the same system. All answers, every question you could ask here, there's an equivalent question there that has the same answer.
You can still tell the difference between a black hole and a quantum liquid.
No. So in different regimes, in different circumstances, this will be the right description. In other circumstances, that will be the right description.
So I could shock some people and say, what we find up there is really a quantum liquid rather than...
Yes, that's correct. Yes, it's correct.
I'm not going to cut off the questions if you don't want me to cut off the questions, but I suspect you're getting tired.
Yeah, some people are leaving, so maybe.
Yeah,
I'm happy to take people when they come and ask me questions.
Yeah.
That'd be good.
So, first of all, I want to thank Sean. I learned a lot from these lectures, and I'm sure you did also. So let's first of all thank Sean.
For more, please visit us at stanford.edu.